Yamu, please get us underway.
Okay. Welcome to LISA Symposium 14. You are now watching the parallel session, Multi-Messenger Astrophysics and Supermassive Black Holes. My name is Kiwamu Izumi. I am the chair of this exciting session today. We have 5 speakers lining up today, namely Alberto Mangiali and Martina Toscani and Elisa Bortoles and Kelly Holly Bockelman and Nathan Stain Lee. So before getting into the talk, I give you an idea of how you raise questions. So the questions may be submitted via the chat at any time. And if you wish to ask a question verbally, please raise a hand or include a comment with your question on the chat. And questions from the live stream on YouTube are also welcomed. And all questions will be answered at the end of the presentation. So thank you so much for watching. So let's get into the talk. So the first speaker is Alberto Mangiali from APC Paris on the multi-messenger synergies with LISA counterparts, prediction and cosmological prospects. And you get 15 minutes for the talk, and I give you a heads up once you spend 12 minutes, meaning you have 3 minutes left.
Okay.
Are you ready, Alberto?
Yes, you should see my slide now.
Yes, and yeah, that's good. So Alberto, please go ahead with your slides.
Okay, so hi everybody, I'm Alberto Mangiali, postdoc researcher di Laboratorio d'Astroparticule and Cosmology, and today I'm presenting some results based on paper that we recently put on the archive about multi-messenger synergies with massive black hole binary LISA. So we start with a quick introduction. I will present the model for the electromagnetic counterpart that we have and give you also the number of electromagnetic counterparts that we expect. And in the end, I will just discuss some cosmological prospects that we can do with this type of sources. So let's start with a quick introduction. We see that we can distinguish a black hole into different populations. So we have the stellar black hole from 5 to 100 of solar masses that are the one that LIGO Virgo are currently observing in binaries. And then we have the population of massive black hole from 10 to the 5 to 10 to the 10 solar masses that we currently think reside at the center of galaxies. So the
Alberto, I'm sorry. Could you turn up your volume a little bit? Your voice may be a little bit shy.
Sounds better?
Yeah, it's better.
Okay. So the idea is that when two galaxies merge, the massive black hole binary that in their center form a binary and eventually merge, emitting gravitational waves. And in mid-2030s, LISA is going to observe the gravitational wave from the coalescence of this massive black hole binary. So well, here on the right, I guess that you are all familiar with this picture, but here you are looking at signal-to-noise ratio in redshift and total mass of the binary system. And you can see that there is a range of masses from 10 to the 4 to 10 to the 7 solar masses, where we will actually be able to observe the entire population of merging massive black hole binary in the entire universe. And we want to look at massive black hole binary at least for 3 good reasons. Well, from an astrophysical point of view, we want to understand how these massive black hole binary form and evolve across cosmic time. From a multi-messenger point of view, these are key sources because they are expected to be surrounded by gas. So an electromagnetic counterpart can be triggered by the interaction between the disk and the binary. And finally, we know that gravitational wave carry information on the luminosity distance of the source. So for example, if we can get the redshift information from an electromagnetic counterpart, we can combine the luminosity distance and redshift information to constrain cosmological parameters. So we started this project with the idea of improving the previous results done by Nicola Tamanini in 2016. So we want to estimate the number of electromagnetic counterparts that we expect over a LISA mission and to see what type of cosmology we can do with these sources. So we performed two key improvements with respect to the previous work. So we improved the modeling of the electromagnetic counterpart. I'm going to discuss about it shortly. And we performed the parameter estimation of the gravitational wave signal with a Bayesian code developed by Sylvain Massart, Elisabetta. That is actually quite expensive from a computational point of view, but it's actually close to the realistic case. As a starting point, we need a population of massive black hole binaries. So there are huge uncertainties on this type of population. So we have three different models to bracket our uncertainties. We have a light model where black holes start at 10 to the 3 solar masses, a heavy model where black holes start around 10 to the 4, 10 to the 6 solar masses, and then a heavy no delay models, which is actually the same of the heavy one, but we remove the delay between the galaxy merge and the massive black hole binary merger. Without entering details, you can see this model as an optimistic one because it provides many more massive black hole binary mergers. We also don't know what type of electromagnetic counterpart we expect from these events. So when you do not know the type of electromagnetic counterpart, you model in all the possible band. So we model the electromagnetic counterpart in optical, radio, and X-ray. And clearly, you have to take into account also some telescope to observe this counterpart. So for example, for optical, we can use LSST or Vera Rubin in future. In this way, we can both identify the galaxy and get the redshift. The redshift in our case is important because at the end, we want to do cosmology. For radio, we have SKA, with which we can identify the galaxy, and then get the redshift, for example, with ELT. For X-ray, we consider Athena. There has been discussion about the scoping of Athena mission, and but actually there is not yet been defined, so we keep the standard configuration of Athena. So again, in X-ray, we can just do identification, and then we can get the redshift with ELT. We also had two variations. So we include the possibility of AGN obscuration. So the possibility that the same gas that is producing the electromagnetic counterpart is also absorbing a fraction of the radiation. And we also take into account the possibility of a collimated radio emission, because in the original paper, they assumed just an isotropic radio emission. So here we try to improve a bit, taking into account a jet with 30-degree opening angle. So this scheme summarizes our procedure. So we start really from the raw catalog, so the number of massive black hole binary merger in here, plus the property of the gas and of the host galaxies. We computed the detectability of the gravitational wave signal. So we select all the system with SNR larger than 10. On this subset, we evaluated the detectability of the electromagnetic counterpart. So we just select the system whose counterpart can be detected in optical, radio, or X-ray. And then on this subset of events, we perform the parameter estimation to have an estimate of the sky localization of the source. So in this way, at the end, we get the rate of electromagnetic counterpart, which in our study are defined as system with SNR larger than 10, electromagnetic counterpart detectable, and sufficiently well-localized sky position, depending on the telescope. So we also have two different scenarios, maximizing one and minimizing one, to, again, bracket our uncertainties. In the maximizing one, we neglect obscuration and we assume isotropic radio emission. In the minimizing one, we have obscuration and we include a collimated radio emission with an opening angle of 30 degrees. We found that, as you will see, these are the two properties that are actually most affecting our estimate. So now we can start looking at the distribution. So for example, here the blue dot dashed line corresponds to the total catalog, and the solid blue line represent just a system with SNR larger than 10. And as you can see, for example, in the heavy model, we are able to recover the entire catalogs. In the light model, we are missing a fraction of light and high redshift events. This is expected because LISA is not really sensitive in this region. Then we can apply the requirement on the detectability of electromagnetic counterpart, and in this way we can select a system at a redshift smaller than 8. And in terms of total mass, we select a preferentially system at a large total mass value because typically they have more gas, so the electromagnetic counterpart is brighter. And then we can apply the requirement on the sky localization of the source. And you can see that in this way, again, we are losing a fraction of system. So for example, here you can compare the dark dash, the green line with the solid, the bright line. And you can see that the loss is particularly significant for light model. Again, it is expected because since the system are light, the parameter estimation is not going to be actually really great. And we can also look at the magnitude or fluxes that we expect from the subset of electromagnetic counterpart. And as you can see, the magnitude, for example, here in optical on the upper left, the magnitude are all above 25, 26, and you can also see that when we include obscuration, the number of electromagnetic counterparts dramatically decrease. For Athena, the peak in flux is at -15, but clearly it extends also to lower fluxes. And you can also see that there is a dramatic decrease when we move in SKA from the isotropic case to the case where we took into account an opening angle of 30 degrees. So bottom line of this slide is that we expect a few and faint sources in Fourier. And to be more specific, here on this slide, you see the number of electromagnetic counterparts for the different strategies. So let's just look at the heavy model for simplicity, here the middle line. You can see that, for example, without obscuration in Fourier, in optical, we have something like 3 electromagnetic counterparts. But if we include obscuration, the number goes below 1. For SKA, we have 15 electromagnetic counterparts in the isotropic case. But if we include, for example, the opening angle of 30 degrees, we have 3 electromagnetic counterparts. For Athena, we have 3, 4 electromagnetic counterparts without obscuration. But again, if we include obscuration, the number goes below 1. So you can see that indeed there is a dramatic decrease when we include the obscuration and the radio jet. Here on this table, you can see the number of electromagnetic counterparts when you combine the different strategies. So taking into account that maybe the same events can be observed with different instruments. And again, overall, we expect 15 electromagnetic counterparts in the heavy model, and in the maximizing case, and the minimizing one, we have 2, 3 electromagnetic counterparts. So during this work, we also have to deal with multimodal events. So multimodal events are systems whose sky posterior distribution is indeed multimodal in the sky. So here there are a couple of examples. So for example, here on the left, we have what we call the unimodal events. Just because, as you can see, the sky posterior distribution is a nice ellipse in the sky. So here the blue contours represent the results from the Markov chain Monte Carlo analysis. The dark ellipses represent the results from Fisher, and the black square represent the actual binary position. So you can see that, for example, for unimodal system, everything behaves well. Then we have what we call bimodal events or two-modes events, in the sense that these are events whose sky posterior distribution presents 2 different modes in the sky. And well, as you can see that the Fisher by construction is able to recover just the single binary, just one spot of the binary, but the posterior distribution actually gives 2 different modes. And then we have what we call 8 modes events, because for this system we have 8 different spots in the sky, and just one of them is the 2-1. And there is not much that we can do about these multimodal events. We know that they are going to be present in the analysis because these arise from the degeneracies inside the Lisa pattern function, or due to the fact that we do not have enough signal at low or high frequency. And as you might guess, this system poses a serious issue when you want to look for electromagnetic counterpart, because clearly you have to look at different spots in the sky. However, we also found some.
You have 3 minutes left. Sorry.
Thank you. So, for example, here on the left, I'm showing the probability for the 2 modes events in the primary and the secondary mode. So here the primary is the true one, where actually the binary is, and the secondary one is the spurious one, the fake one. And as you can see, the primary mode, the 2-1, is actually contains always more probability than the secondary one. So we say that overall we should be able to spot the true binary position just looking at the probability. And this is actually quite interesting because on the other hand, if we look at the contribution of these two modes events to the total number of electromagnetic counterparts that you expect in Fourier, you can see that actually the contribution is not that negligible. So it's around 20–30% of the total number. On the other way, for H-mode events, you can see that the number of electromagnetic counterparts that we expect is less than 0.5 in Fourier. So already from this, we can say that H-mode events can be considered as negligible in the estimate of the electromagnetic counterpart. This is actually quite useful because, for example, if we look instead at the probability for H-mode events, we can see that for H-mode events, all the modes are more or less equiprobable. So here you can see, well, this corresponds to the two binary position, and all these 7 are the spurious one. As you can see, the probability is more or less around 10% in all cases. So they are equiprobable, but they are not really contributing significantly in terms of numbers. So bottom line is that, again, multimodal events do not affect significantly the number of electromagnetic counterparts. So finally, just some preliminary results on cosmology. Here you can see the posterior distribution that we have on omega matter and H naught from one realization of the maximizing model. So here we have something like 14 electromagnetic counterpart, and you can see that we are able to constrain H at around 4%. This is an average realization. But for example, taking into account that we also have the minimizing model where we have a less electromagnetic counterpart, I would say that at the end we should be able to constrain H naught around 10%. So here my conclusion. My conclusion is that multi-messenger and cosmology with massive black hole binary is going to be challenging. The peak of the distribution in terms of redshift is around redshift 2. And the typical binary that we are going to observe will have total mass of 10 to the 5, 10 to the 6, maybe a few 10 to the 7. So the electromagnetic counterpart is not going to be extremely bright for this type of sources. So we need to accurately plan any follow-up strategies in order to maximize the number of counterparts that we can observe. From cosmology, this is still preliminary results, but probably we'll be able to constrain H naught around 10%. But the idea is that clearly we can combine massive black hole binary with other type of sources in LIDA, so like stellar black hole binary and Emery. Then we talked about that a couple of days ago. In order to construct this sort of cosmic distance ladder in terms of gravitational wave and to constrain cosmology. So thanks for your attention, and I'm happy to take any questions.
Thank you so much, Alberto. So the floor is now open for the questions. If you have any questions, please raise your hand or you can type it in the chat. Okay, I see a chat window, a question from Danny saying that if there is a simple explanation for that, how did you choose the values of the jet collimation angles, meaning 6 and 30 degrees?
Yeah, there are basically different models in that you can find in the literature, and we just took the two representative value. I didn't discuss the 6 degree because clearly, if you take into account a 6 degree, you can see from this table that we do not have any electromagnetic counterpart. So we just took 30 degrees because we found it in the literature, honestly.
Okay, I see a hands up from Alberto Cesana. Would you be able to speak up?
Yeah, can you hear me?
Yep.
Yeah, a couple of short questions still also related to the counterparts. In the case of the radio emission, did you consider also the possibility of having a compact radio core? So in that case, you know, the compact radio core might be essentially isotropical emitting, so you won't need collimation, you know, a collimated jet pointing at you. Of course, the downside is that this might be less luminous. So I was wondering whether you consider that.
I think no, because for the radio, basically we assume the same model of Nicola Tamanini. So
okay, so there's no.
Yeah.
And if I may, can you say something about the obscuration that you assumed for the X-ray? What did you assume for, like, as NH? Maybe you said it.
Okay, well, okay, they're just a reference. Well, basically, we took the expression from WEDA 2014 that give us the fraction of obscured AGN. So from basically from the catalog, we have the information on the acritic gas. The expression here from WEDA basically are based on the X-ray luminosity. So the idea is that we start from the catalog, we computed the X-ray luminosity, and then we use this correction fraction to take into account obscuration.
Okay, thanks.
But we have a distribution of hydrogen column density that comes from this paper. Yeah.
Okay, thank you.
Okay, and I take another question. Viviane, yes,
yeah.
please.
Yes, I have a quick question on slide 9. I saw that the heavy delay and no delay model gave the same number of counterparts in the minimizing model. Can you give an intuition for this?
Yeah, the point is that, as I said, it can be considered as an optimistic model in the sense that provide many more massive black hole binary merger. But the point is that you have to look where these mergers are located. So, for example, if we go, well, okay, we can just take this slide. So the point is that it provides many more massive black hole binary merger, but typically at high redshift. And also the amount of gas surrounding this binary is not typically that large. So at the end, you know, the fact that you have, a lot of massive black hole binary merger, but a high redshift at the end does not contribute significantly to the number of electromagnetic counterparts.
Okay, I see. Yeah, thanks.
Okay, I think it's time to move on. So thank you so much, Alberto, and let's thank the speaker. So the next speaker up is, let's see, Martina Toscani from Laboratoire des to Infinites on tidal disruption events as way to study black holes. So please go ahead.
Okay, thank you. Okay, so can you see my screen? Yeah?
Yes.
Okay. So good morning, everyone, and thanks for this opportunity. My name is Martina, and I am a postdoctoral researcher at Laboratoire des Infinies in Toulouse. And today, I would like to show you what has been so far my main research topic, that is the study of tidal disruption events, in particular as a way to study, to better understand black holes. So let me start from the beginning. And okay, what is a tidal disruption event, for short TDE? Well, a TDE takes place when a star orbiting around a massive black hole gets disrupted due to the black hole tides that overwhelm the stellar self-gravity. After the disruption, we have that roughly half of the stellar debris are expected to circularize around the black hole and eventually form an accretion disk. We observed these events since the 90s, and so far they have been one of the most powerful ways to detect otherwise quiescent massive black hole through the universe. As a matter of fact, while the stellar debris accretes onto the massive black hole, we have a production of very luminous electromagnetic flares. And to present, we have been able to observe around 100 tidal disruption events, mainly in two bands of the electromagnetic spectrum, optical and X-ray. Yet, we can study these events also through other possible messenger. Neutrino, for example, because we expect the production of a high energy neutrino from the later stages when we also have production of jets in some cases. And actually there have been some potential candidates of astrophysical neutrinos from tidal disruption events. And finally, they also emit gravitational waves. In particular, we expect tidal disruption events to produce gravitational wave radiation during the whole process, But here in this talk, I will just focus on the gravitational wave contribution from the disruption phase, that is the signal generated by the time variation of the black hole star mass quadrupole. So let me say something more quantitative of this signal. It is a monochromatic burst with a maximum strain and frequency that are approximated by this two analytical formula that you can see on the top of the slide. So for typical values of the parameter that describe this kind of system, we have that the strain H peaks around 10 to minus 22, while the frequency span from the milliards, that is the frequency window where LISA will be most sensitive, to the deteriorates, that is the frequency window where we hope there will be future deteriorates observatories. So at this point of the presentation, let me stress that so far we have already detected tidal disruption events, mainly for electromagnetic radiation, and this radiation allows us to see the later stages of the disruption. Yet in the future, we will also observe tidal disruption events with gravitational waves, and thus, for the first time, we will directly access the disruption phase of the star. Yet, before observing tidal disruption events, we need to know in advance how their signal looks like and also what kind of information we can extract from this signal. In order to answer to this question, to face this problem, I have implemented a tool for the numerical derivation of gravitational wave emission from tidal disruption events. So I implemented this tool in Phantom, which is a smoothed particle hydrodynamics code, particularly well suited for three-dimensional simulation of non-axis symmetric systems like tidal disruption events. And basically my algorithm is the numerical transcription of the quadrupole approximation for gravitational wave emission. So I created this tool that on the fly during the simulation is providing the values of the polarization amplitude H plus, H cross as a function of time, and I started to use this tool to describe the gravitational wave signal from tidal disruption events. So in this plot, you can see the gravitational wave signal that we obtain for a sun-like star disrupted by a static 10 to 6 solar mass black hole at 20 megaparsec from us. And we are observing the system face on. Actually, these results are quite reassuring because they both agree with the analytical estimates that I showed you before, but also with some previous results in the literature, like the one of Kobayashi et al. In 2004. Once I created this tool, I started to use it in order to investigate the parameter space that actually describes tidal disruption events and to see how different values of the parameter involved can affect this signal. So if you are interested in this, you can find all the results of this investigation on this catalog online. And just to show for instance, one of the information that, at least in theory, we can extract from the observation of this signal, this is the black hole spin, because we can find that the different black hole spin affect the gravitational wave signal from a tidal disruption event. And in particular, we have that this gravitational signal increases for higher values of the black hole spin in case of retrograde orbit, while the opposite trend is observed in case of prograde orbits. Okay, so now that we have a tool that allows us to derive the gravitational wave signal from a tidal disruption events for any configuration of the parameters that we want, we also need to understand how many tidal disruption events we actually expect to see in gravitational waves. So how many detection? Well, let me say that the answer to this question changes a lot depending on the interferometers that we are considering, because I anticipate that if the HRS observatories like the SIGO will become a reality, we will observe thousands of tidal disruption events per year up to cosmological redshift in gravitational waves. But what about LISA? Well, the situation about LISA, at least in the case of main sequence stars and supermassive black holes, seems to be a bit more pessimistic, as you can see from this plot, where on the vertical axis, I show the number of tidal disruption events in 10 years, assuming that 10 years is the lifetime of the LISA mission, while on the horizontal axis, I show the signal-to-noise ratio. The vertical red line corresponds to signal-to-noise ratio 1, and the pink horizontal line corresponds to 1 tidal disruption events in 10 years. So you can see that the curve, the blue curve, actually is above the threshold of 1 tidal disruption events in 10 years only at low signal-to-noise ratio, where basically we cannot expect to have a detection by LISA. So the situation seems a bit dramatic, but we can see if gravitational lensing could improve this scenario. So what is gravitational lensing? Well, we have this effect when there is a massive object, that is the lens, between us, the observer, and the source that is emitting the signal we want to study. So this massive object is actually bending the surrounding space-time, and this causes a deviation in the path of the signal that we want to observe. In particular, here I focus on strong lensing and on a very interesting consequence of strong lensing, the magnification, that is the amplification of the signal. So how can I understand if my signal is magnified and how much is magnified? Well, I need to calculate this quantity, which is given a population of sources, in this case, at a distortion events, of course, at a given redshift, given a distribution of lenses, I want to calculate the magnification distribution. In order to calculate this magnification distribution, I need to derive 2 main ingredients. One is this small p, which is basically the magnification probability density function that for a fixed redshift that depends only on the distribution of lenses that I choose. So here in this quantity, there is no information of the astrophysical source that I want to study. In this case, so in this plot, I am obtaining these curves considering as lenses galaxies, but then in future I want to consider more sophisticated lens distribution to calculate this quantity. And the second main ingredient that I need to calculate is the number of observable tidal disruption events per unit of redshift bin as a function of mu, the magnification factor mu. So you can see in this plot that this quantity, the n over the z, actually is decreasing for higher value of the redshift, which makes sense because I have a cut in the signal-to-noise ratio, but is also increasing for higher mu, which is also reasonable because for higher mu, the signal-to-noise ratio limit for detection becomes smaller and smaller. So with these 2 main ingredients, I can calculate this probability, the magnification probability distribution. And here you can see for different redshift the values of this distribution. And from this kind of plot, I can get 2 main results. One is assuming that I observe a tidal disruption event at a specific redshift, like for instance 0.28, I can calculate what is the probability that my tidal disruption event is actually magnified more than a specific value. Like for instance, more than 16 is 27%, more than 100 is 2%. And then the second thing that I can calculate from this plot is at each redshift, I can calculate an average magnification factor so that actually I can estimate what is the number of tidal disruption events above the signal-to-noise ratio threshold when I assuming a distribution of lensings. But so far, I still don't have this number because it's work in progress and I still need to finish the calculation. So maybe lensing can actually improve the situation for detection of tidal disruption events with LISA, and for sure will be interesting also for the shared observatories. But before concluding this presentation, let me show also another interesting calculation that can be done with tidal disruption events and gravitational waves. We can provide an
Martina,
estimate.
you got 2 minutes left.
Okay.
Sorry, 2 minutes left. Yeah.
Yeah. We can provide an estimate of the gravitational wave background from this population, and it is what I did, in particular distinguishing between nuclear tidal disruption events, where I assume main sequence stars disrupted by supermassive black hole in the course of galaxies, and the globular tidal disruption events, where I assume white dwarfs disrupted by intermediate mass black hole in globular clusters. So I did the calculation for these two classes of tidal disruption events, and what I got, mainly two results. The first is that for both the classes, as a consequence of the impulsive nature of the gravitational signal from a TD, this background signal is proportional to the frequency to -1/2, which is a peculiar feature of tidal disruption events. And then the second result is that while the background from main sequence stars actually is in a part of the frequency window where there are no interferometers sensitive enough to detect it, the situation can be different if we consider the background from globular tidal disruption events, so white dwarf and intermediate mass black hole. It can be very interesting for the shared observatories, and a possible detection can constrain the distribution of intermediate mass black hole in the universe up to redshift 3. So let me conclude just showing the final slide with the take-home messages, and I thank you for your attention.
Thank you so much, Martina. So we can now take some questions. Okay, I see a hand up. Shiho, you are the first.
Yeah, nice talk. And so, yeah, about gravitational lensing, and yeah, you don't have a result yet, but just wondering anything by the amplification. Can we detect prompt X-ray emission? Some same factor X-ray emission going to amplify, and if we have X-ray detection slide to the maybe help detection of gravitational wave itself, and considering future X-ray emission and amplification factor, any chance we can detect X-ray flash at the moment of tidal disruption?
Yeah, I mean, if I understand correctly, in this case, I was talking, of course, about gravitational lensing of the gravitational wave signal, but my idea is to actually complete them.
Yes, but the same process, same physics.
Exactly.
Apply,
yeah,
right?
exactly. Yeah, actually, this is what I'm planning to do, to complete also the calculation with gravitational lensing of the electromagnetic counterpart and see what I get. Yeah, I agree.
Okay. Yep. Yeah. Okay. Yeah.
Yeah, that's pretty interesting. Okay. So the next, Roberto, you are the next. Can you speak up?
Yes. Can you hear me?
Yes.
Yeah.
Thank you. Thank you, Martina, for the nice talk. So I have two questions, both related on lensing. First question is, for the lens distribution, are you using a catalog of observed lens, or it's like a simulation? Second question is, you seem to limit yourself to redshift up to 1, which I guess is due to the fact that if you put the TD farther away, the SNR is smaller, but it's also true that the lensing probability is higher. And so I was just wondering if redshift equal 1 is really where these two effects compensate each other.
Okay.
Thank you.
So as for the first, so these are for the moment just preliminary results where I am assuming a distribution as like a Schechter function with Z dependence, but I actually aim to use the Illustris catalog, which is a simulation actually of galaxies as a lens distribution. And I can also further improve the lens distribution using some constraint simulation that can actually map better the universe at a low redshift. As for the second question, well, actually, I also have the results on, up to redshift 10. But I have to say that, at very high redshift, the signal to noise ratio will be very, very low. And also, I mean, it's true that we have a compensation because it's true what you said, that at higher redshift, the probability to be lensed is actually higher, but not in such a way that we can have some very important shift in the signal to noise ratio and then a possible detection by LISA. This is why actually I show in this talk up to redshift 1, 2, I don't remember exactly.
Thank you.
Okay, I have a quick question. So when you compute the TD backgrounds, what kind of IMBH population did you assume?
Yeah, in this case, I assume that the population of IMBH is in the range 10 to 3, 10 to 5 solar masses, and I assume in them to live in globular clusters, where initially I assumed that each globular cluster has one as an occupation fraction of 1 of an intermediate mass black hole, and then of course I reduce this number to see how this estimate can change. But for instance, there are actually, I think, many ways to improve this calculation, considering also intermediate mass black hole in dwarf galaxies, and maybe even I think I can also go down to 100 solar masses as an intermediate mass black hole in the mass range, which is true that it's this signal, the gravitational wave signal is actually weaker for lighter massive black holes, but it's also true that we know, thanks to LIGO Vigo, that these light massive intermediate massive black holes actually do exist, so it can be actually more interesting. There are many fallouts that are possible for this calculation actually, so yeah.
I understand. I just wanted to check out what kind of assumptions you took. Okay. All right, thank you so much, Martina. I think it's time to move on to the next talk. So the next one is from Elisa Bortoles from University degli Studi di Milano Bicocca, sorry. And she is going to talk about gas stars and gravitational waves on the main driver of massive black hole binaries path to coalescence. So Elisa, would you please go ahead?
Sure. Thanks for the introduction. Can you see my screen?
Yes.
Perfect. So, okay, so this presentation, this work has been done in collaboration with my colleagues here in Bicocca, Alessia Franchini, Matteo Bonetti, and Alberto Cesana. And in particular, it focuses on the small scale shrinking of massive black hole binaries. So let's first of all start from the basis. First of all, since we are all interested in LISA here, we know that LISA is sensible to the merger of two supermassive or supermassive black holes, but in order for them to emit a sensible amount of gravitational waves, those two black holes need to get very close. And in order to have two massive black holes in the same galaxy, we expect to need galaxy mergers. But galaxy mergers occur at much larger scales. So we really need to understand how the two massive black holes can shrink from this scale down to the gravitational wave emission stage. And actually, the first seminal work that really tried to understand how this works dates back to the 80s. And the simple feature that was put forward was that dynamical friction, which is a sort of gravitational drag against dark matter, gas, and stars, will basically ferry the binary down to the bound stage, at which the interactions with stars will help the further shrinking, possibly aided by the effect of gas, which of course would give rise possibly also to some counterparts. And then around the milliparsec scale, we would have the emission of gravitational waves and the final spiral. In the last few years, though, this simple picture got way more complex, just because people try to put a more complex physics and more realistic environmental properties and study the binary evolution in this like more realistic context. And you see that we have way more processes compared to what we were expecting before. And in particular, today, what I want to talk to you about refers to the small scale binary evolution. The small scale evolution namely means what happens when the binary manages to be bound in a Keplerian system. And I'm just going to show you what happens if we combine different processes that can actually happen at the same time. I think this is a very important thing to highlight already here, because most studies that try to infer the evolution of binaries in this stage either only assume stellar hardening, so stars to actually aid the binary to reach the gravitational wave emission stage, or other words, just focus on the possible presence of a disk of gas that can also influence the binary evolution. But in fact, especially if we focus on LISA sources, so we target relatively small massive black holes, we expect that both gas and stars would be present at the same time. And so in this work, we specifically wanted to understand what happens when both ingredients are together present in the host system, and also to add the evolution driven by gravitational waves. More specifically, what is stellar-driven hardening, stellar-driven evolution? So basically, when we have a bound binary, each time a star gets close enough to the binary, it undergoes interaction that is typically ending in a slingshot ejection of the star out of the system, and the binary shrinks in the interaction, so that as many stars get close to the binary can shrink further and further. When we have some gas around, even if kind of ironically, some time ago, gas was thought to be the perfect thing to really help the binary shrinking, later work kind of suggested that depending on the configuration of the gaseous disk around the binary and the binary mass ratio and so forth, it is unclear whether gas can actually shrink, or in some cases even expand the binary. And if in some configurations there is this binary possible expansion, this is very important to figure out for LISA, because in principle it could mean that the binary surrounded by gas would never enter the gravitational wave emission stage, because this effect prevents their evolution. Of course, if instead the binary manages to reach a separation small enough, then we all know that we have gravitational wave emission that is very efficient in driving coalescence. So here I'm going to present the ingredients that we put together in this semi-analytical calculation to study the evolution driven by both stars, gas, and gravitational waves. First of all, the stellar-driven hardening is kind of very well understood in the literature, and we have that the derivative of the binary semi-major axis in time scales as minus the semi-major axis squared. This just means that as the binary shrinks and shrinks, the effect of stars in extracting energy get less and less efficient, right? If we have a gravitational wave emission, instead, we probably all know that from Peter's formulas, the derivative of the binary semi-major axis in time scales as minus 1 over the cube of the binary semi-major axis, meaning that we are a sort of runaway process. When it starts, it cannot really be reverted easily. And what do we assume for the gas-driven evolution instead? To be very pessimistic and really explore the worst possible configuration for LISA, we just assume that when there is gas, it can only expand the binary. And in particular, we took this work from Diego Muñoz, which is in agreement with many other works that study the same problem, according to which the derivative of the binary semi-major axis in time, the semi-major axis expands proportionally to the binary semi-major axis. Of course, depending on the normalization of this curve, we can have that gas expansion actually occurs or it can be neglected. Specifically, I want to show you that the normalization of this curve depends on the mass accretion rate of the binary divided by the binary mass. And in particular, in this work, what we assumed is that the binary always accretes at a fixed ratio of its Eddington limit. And we named this ratio as F-ed. The Eddington ratio. We also tried different prescriptions, but we found this to be the worst case scenario for binary expansion. So we stick to this here. First of all, what I want to show you is that just by combining the equations I showed you so far, what we were already able to work out is that gas expansion is expected to play a non-negligible role, so this curve to be above here, only when the binary accretes at a fraction of its Eddington ratio, which is above 10%, and in some cases at lower binary masses even above 50%. So the binary needs to accrete an enormous amount of gas to expand if stars and gravitational waves are also included in the evolution. Also, another important question is that can the binary expand forever? Of course not. And in particular, what we implemented in this work is that the binary stops its expansion as it hits the disk self-gravitating radius. This is basically the radius above which the disk starts developing structures as spirals or start collapsing, and there is no evidence of binary expansion if the disk is in this regime. So we just stop the expansion here. And here is just the dependence of the self-gravitating radius on the Eddington ratio and the binary mass. And also by implementing this further ingredient in our equations, we were basically able to say that there is no possible expansion occurring for binaries whose mass is above 10 to the 8 solar masses, which is not really in the LISA band, but it's at least good to know. And now, instead, what I'm showing you are the evolutionary tracks of binaries that undergo some expansion. In particular, here I'm showing the case of a binary with 10 to the 4 solar masses, total mass, and equal mass. This is a rather low mass binary, but just because lower mass binaries undergo more efficient expansion, we find. So this is sort of, again, a worst case scenario. So what I'm showing you here is the binary semi-major axis as a function of time, binary mass as a function of time, the residence time, so time, how much time the binary spends at each separation as a function of the binary semi-major axis, and mass as a function of the binary semi-major axis. So from those plots, you see that if the binary is not accreting, so the gray line, its evolution is rather smooth and nothing really hinders the in spiral. When we start putting F Eddington to 0.6, we see that the binary undergoes a little bit of delay in its evolution, but it does not actually expand because gas expansion is not strong enough. If we put the binary accreting at the Eddington limit instead, what we see is that the binary does undergo some expansion because gas is efficient in expanding it, it hits the disk self-gravitating radius. It stalls on the disk self-gravitating radius, but in this time, its mass has grown a lot because it's accreting at Eddington. So at this separation in about 400 million years, this separation is enough for gravitational waves to drive its coalescence, so the binary would coalesce anyways, just by increasing a lot its mass. If we put the Eddington the accretion even to super Eddington, so 3 is the value here, everything happens the same, but just faster, because accretion is more efficient, expansion is more efficient. So overall, the binary would just merge quickly compared to the Eddington limit case. This is interesting because what we see here is that in the case of binary expansion, what we have is that not that the binary would not shrink, but instead that binaries in the LISA band would eventually end up in the band of PTA just because their mass could be enhanced so much. And also,
so Lisa,
here,
you have 2 minutes left.
Perfect, thank you. Okay, so here what I'm showing you is the time scale over which all those processes occur as a function of the assumed Eddington ratio. And the different colors mark binaries with different total mass. And in particular, what you see is that as the binary accretes mass at around the Eddington limit, the in-spiral time scale can get larger, but never larger than a factor more or less 10, compared with the case in which the binary is actually not accreting at all. So this just means that the binaries do actually merge in a time scale that is much smaller than a Hubble time, even if they undergo this putative expansion phase. And even more interestingly, this enhancement in the time scale for the evolution could even just mean that we have more time to find them in the electromagnetic band, because if they are accreting a lot, they possibly are even emitting a lot of electromagnetic radiation. Yeah, and so here is my doggy bag for you to bring home with all the key messages. So first of all, I really want to stress that in most LISA binaries, for most LISA binaries, we expect to have the host environment to have both stars and gas. And we need to consider both those ingredients to really understand how the binary evolution proceeds. Second key message is that even if we assume the worst possible scenario, so gas drives the expansion of the binary, this is not dramatic. This does not dramatically impact the time scale over which the binaries reach coalescence, as the expansion gets into a shrinking as the binary accretes enough mass. Also, this expansion phase could, in principle, lengthen the time scale over which binaries can be targeted by electromagnetic surveys. And also, this expansion can put some binaries that were instead in the LISA band into the band of pulsar timing array observatories. And here I stop my presentation, and thank you for your attention.
Thank you so much, Elisa. Any questions? Yes, I see. Nicola, you were the first. Can you speak up?
Yes. Hi, it's Elisa. Yeah. So I have a question regarding basically timescales and lengths, if you want. You were saying that even here at the end, you're saying that binaries might go from the LISA band to the PTA bands due to the expansion, due to the gas accretion. But yes, I didn't understand. Can you clarify actually, are these effects of gas accretion and stellar hardening happening on the same time scales? Because as long as I understood, like stellar hardening was coming before gravitational wave emission could dominate. So I was expecting this to be before the binaries were in the PTA or LISA frequencies, let's say.
Okay, yeah. So basically here, of course, in the initial phase of the evolution, we just have stellar hardening and possibly also this effect of disk expansion that are actually playing a role. But the key point here is that at some point the binary would stall at a separation, and for that given separation, the binary mass would increase so much just because of its very high accretion rate that this separation is enough to start emitting a lot of gravitational waves and then merge. And so this is basically in the PTA band if it accreted so much, while as it was undergoing the initial shrinking and then expansion, this was not really in the gravitational wave, not so much in the gravitational wave driven regime.
Okay, thank you. So
at least for this case, yeah.
No, I understood now the concept, because the time scale is changing because the masses are changing, because they are increasing. Okay.
Yeah.
And can I have a follow-up question actually on this? If this is the case, actually, I would expect a lot of binaries to stall at some specific distances, or let's say some specific ranges. So I would expect this maybe to give a bump in PTA stochastic backgrounds spectrum, let's say, or any other effects. That's maybe interesting to look at.
Yeah, so absolutely. So this is a very interesting point. In here, what we just assumed is that this would be the self-gravitating radius. But in principle, actually, the real scale at which you expect the binary to stop expanding is the scale at which the disk is not there, or all the gas that was around was accreted. And this is really, at that point, gets really system dependent, because in this configuration we just assumed the worst case scenario, so that there was an infinite amount of gas in the system that could be accreted by the binary. So I guess that particular scale at which this stalling would occur should we more realistically the scale at which the disk of gas stops existing or is exhausted because of accretion, if it makes sense.
And this is not PTA frequency, for example. Just
Sorry?
to make sure, this is not in the PTA frequencies.
This is a good question. I guess in order to really understand this, we should put all those processes into like a realistic environments with like depending on their initial mass and so on and so forth, and really see also assuming an amount of gas in the central region, like how much we can have this expansion going on. But I think this model is a little too simplistic and pushing to the limits to really have a clear answer for that.
Okay, thank you.
Okay, although I see a hands up from Alastair, I think it's time. I think it's time to move on to the coffee break. So, thank you so much, Elisa.
Thanks.
And let's have a coffee break and meet at I think 10:15 in UTC, and meaning it's 19:15 in Japan. I guess it's only me. Anyway, so. Stay tuned, and that concludes the first half of the this parallel session. Thank you. Okay, shall we resume the session? So welcome back to the parallel session, multi-messenger astrophysics and supermassive black holes. So the next speaker is Kelly Holly-Bockelman from Vanderbilt University, talking about the handy massive black hole merger timescale, scaling relations for subgrid models. So Kelly, are you here?
I'm here, but I'm trying to find my my keynote just crashed, so I'm trying to bring it back up again.
Okay.
Could we take 1 or 2 minutes, or maybe go to the next person? Give me 1 second.
Sure.
I think we've got enough time that we could probably give you a few moments, Kelly.
Oh, thanks.
Yeah, take your time.
I'm just herding humans in the background here. So it's a busy office.
I'm sure it is. Okay, can y'all see me? Good morning for me. I am trying to get
Actually, they don't see you
up.
at this moment, Kelly. Okay, they can see you now.
Yep, perfect.
Great. And can you see it if I switch to the next slide?
Yeah.
Perfect. All right, folks. All right. Thank you. Today, I want to talk to you about some work that we're doing to try and make a little bit of a relation or an equation or a handy, a handy relation for folks who want to figure out what black hole merger timescales are, because it's pretty different in the LISA regime. And let me just take a step back and explain. The picture here is, if you ask an astronomer what a massive black hole is, they'll probably think of something like this. This is Centaurus A. It's a giant elliptical galaxy. The black hole jets sort of suffuse the entire galaxy. As you can see in radio, this black hole is 1 billion solar masses, and that's not the kind of thing that a LISA astronomer will think of. So let me just pause and let y'all revel in the fact that LISA black holes are quite different. As Jesse sort of mentioned in the plenary talk on the first day, LISA black holes live in an entirely different type of galaxy and in totally different systems. So here are some Milky Way mass black holes, 10 to the 6 solar mass black holes. They live in spiral galaxies that don't have bulges in them at all, and they're revealed in X-rays. They can live in low surface brightness galaxies like Malin 1. Here's another Milky Way mass black hole as well. They live in dwarf galaxies. This is a very famous one by Amy Rines, Hanai's 210. It lives in something that's kind of like the mass of the Large Magellanic Cloud. Here is another recent finding in a little satellite galaxy called Leo 1. There's 1 million solar mass black hole. And at the center of the Milky Way, there's 1 million solar mass black holes. So you can see the huge dynamic range of places in which LISA black holes live. Here are some other dwarf galaxy findings, again, sort of 1 million solar mass black holes, and they tend to live off center of their host galaxy. So these were called wandering black holes in dwarf galaxies. There's some other even lower mass black holes found sort of in the outskirts of galaxies. There's one of the early ones, HLX1. Here's a very recent one. This is Andromeda. It's got a 10 million solar mass black hole. It has a little satellite galaxy that has an intermediate mass black hole in it. And same thing for this galaxy. This little tiny satellite shown brightly in X-rays because of a tidal disruption event. Oops. That tidal disruption event, here's an artist's rendition of it. And it allowed us to sort of estimate what the mass of that black hole is. And it's even lower mass, again, sort of in the Milky Way regime. Of the sort of large galaxies, one characteristic is that many of the black holes that are found in LISA that sit at the centers of galaxies live in the type of galaxies that have nuclear star clusters. So this is an example of a nice spiral galaxy that at the center has a nuclear star cluster. Here's another. This is a great review should you want to learn about nuclear star clusters. The big deal is that if you look at the stellar mass of a galaxy and the fraction of those galaxies with nuclear star clusters, they're pretty huge. Roughly 80% of the galaxies that are kind of in the stellar mass range to host LISA black holes host nuclear star clusters. And those have very different properties. So nuclear star clusters, you can think of them as like a super globular cluster. They are the most dense stellar objects in the universe. And so this is an example of that. Sorry, it's in surface brightness, which is kind of like a proxy for stellar surface density as a function of radius. And you can sort of see if this particular galaxy just had a flat kind of density profile, stellar surface density profile, that's what it would be. But again, sort of rise 4 orders of magnitude in stellar surface density. So super dense, but also they're flattened and rotating. So what this plot shows you is the fraction of the kinematics that goes into rotation versus velocity dispersion. And so this would be highly rotating, and this is not. These are all galaxies with nuclear star clusters, and here's the ellipticity, or sort of the flattening, the 2-dimensional flattening of that system. So they're flattened and rotating, either co or counter, depending upon what it is interacting with. Okay, so let's put that in the context of merger timescales for black holes. So as you all know, the black holes may exist in 2 different galaxies. As the galaxies merge, the black holes come together first through dynamical friction and then through 3-body scattering. And that's the part that my team and I work on and have for years. So when the black holes become bound, the only way that they can get closer together is by basically bleeding energy and angular momentum from the orbit, either through gas or through stars. And we concentrate on stellar interactions. So the black holes can do a few body scattering, sort of kick a star out or give a star more energy, and then the orbit becomes closer. And that folks used to think that this took forever. It's because of this thing called a loss cone. So just really quick, this is angular momentum. And so essentially circular orbits are up here, radial orbits are up here, because it's sort of a ratio of angular momentum to the angular momentum that you would have at the same energy for a circular orbit. This is energy, but black hole is this way. And so you see a whole bunch of stars here, and you see this little empty space. And that is because in this region, all the stars that could interact with the black hole have been kicked out. This radius right here is sort of the hardening radius, that radius where black holes can become closer if they kick stars out. And you can see anything sort of in this region in energy angular momentum space has mostly been kicked out. These stars have been kicked, but they can come back. So you can see the loss cone is evacuated really quickly in this model here, which was of a static spherical model. And that's the problem. Because as you'll see, once you relax those really stringent criteria of a perfectly spherical system that's static, et cetera, then that loss cone can get refilled, but we had to show it. And this requires a very computationally expensive approach. And I can talk to you about how taking shortcuts can lead you to a misleading answer. So I could talk a lot about that, but maybe I won't, because I just want to tell you what we got. Nonetheless, what we did was we built a model of the galaxies that were less perfectly symmetric. In this case, like our very first case, we just built something that was static, but axisymmetric. It was not rotating, and then we basically allowed the black holes to sink closer and closer together due to few body interactions. But the interactions were calculated directly without kind of shortcuts with smoothing or fixed potentials or statistical techniques to figure out the scattering rate. So anyway, details about that there. And what we found, and what lots of people found later and even earlier, was that as soon as you relax this concept of symmetry, so allow the galaxies to be axisymmetric or triaxial or rotate, then entirely different orbit families are allowed in those potentials. And so here's an example of orbits that we found in a nice non-rotating axisymmetric galaxy. They're called saucers. And we also found pyramids and a bunch of other cool orbits. But the big deal is that they're centrophilic A, and that means they go towards the center, quite easily, and so they can fill the lost cone pretty well. But also in many cases, especially in triaxial systems, the orbits don't have to conserve angular momentum at all. So they kind of sweep through that lost cone and they can refill it really quickly. In fact, so quickly that we consider the lost cone always full in this case. So in the case that we showed, 60% of the stars were this type of orbit that can interact with the black holes really efficiently. So just let you know, this thing that you may call the final parsec problem really isn't a problem. What it means is that you've made a system, or you've assumed that that your black holes are orbiting in a system that is spherical and static and so forth. Okay, so yeah, so if we had roughly 2 10⁶ solar mass binaries, then we calculated that it would take roughly 300 million years to merge in this very equilibrium type galaxy, but just flattened. And then we, over the years, started making things more complicated by adding rotation and by doing triaxial systems. And let me just walk you through this plot just really quickly. This is the inverse of the separation between the black holes. Sorry, I know it's weird, but this is really close together. This is far apart. Around about here is the separation in model units that it would take to pass from 3-body scattering phase to the gravitational wave merger regime. And you can see in a spherical system, you never reach that case. You do barely reach it if you're just axisymmetric. And if you're rotating, then the orbits shrink even faster. And just a word about why it's so computationally expensive. This marks the evolution of the black holes when you have a differing particle number. And interestingly enough, you can see when you have very few particles, it looks like the system shrinks faster, right? And as you add more and more particles, then the system well, it looks like it takes longer to merge, but that is all because of numerics. Because you can also refill this lost cone just through noise, just through this thing called artificial 2-body scattering that comes from a simulation that has a lot of numerical noise. And so once you add particles, you sort of go better into the collisionless regime and you can resolve the physics. Anyway, that's part of the reason why these are so expensive, because you need a couple million particles to accurately resolve the physics. Anyway, some cool stuff.
Kelly,
when you add
have
rotation.
3 minutes left. Sorry,
how
3
many
minutes left?
Perfect.
3.
I will not tell you the cool things. So what we did is, with a whole suite of simulations in which we built the galaxy models to match observations from things like the Sirsic profile and rotation, etc. We calculated coalescence times and so forth and tried to find relations. And one easy relation that folks already knew was that the shrinking rate the binary is related to the stellar density, and that's nice here. The dots correspond to whether or not the system, the black hole came in co-rotating or counter-rotating, or the gray, the system was not rotating. But that coalescence time isn't as correlated with stellar density as we thought. So it's much more complicated. So if you have systems that come in co-rotating, their coalescence time in log of gigayears is much longer than if the system is counter-rotating and the eccentricity is high at the end. So you can see a lot of scatter here, but you also sort of see two paths. And the big deal is that this scatter means that we've got some higher manifold going on, and that these are projections of that higher manifold. So we see the coalescence time, log of the coalescence time, as a function of binary black hole mass. And again, you sort of see two categories, but a lot of scatter. One clue comes into the final eccentricity. So the final eccentricity of the system really matters in determining the coalescence time. Even if something has a high scattering rate, if it comes in at a low eccentricity, then it takes much longer to merge. That we sort of knew, but it's nice to see it plotted here. And finally, this is our handy relation. I'm holding you in suspense because this is not published yet, but let me show you. So this is given the principal component analysis regression. We have, I think, 5 principal components here. And with that prediction, that is the yellow, versus a sort of one-to-one relation, we are able to predict the black hole coalescence time as a function of things that astronomers observe. Things like V over sigma, the rotation, the Sirsic index, which maps to density profile, remember, the black hole mass, the eccentricity, as we showed you, was a big component, and the galaxy size. So stay tuned, but I think this will be really useful to use for folks who are doing simulations, for example, and they want to model black hole merger rates as a global thing, but they don't know how much time to assign for a black hole merger timescale. This will definitely help. So you can go look at a galaxy and predict how at least for realistic galaxy shapes and sizes and black hole masses, how long they take to merge. Okay, there, done. Thank you.
All right, thank you so much, Kelly, for the interesting talk. So I think the floor is open for the questions. Oh yes, Roberto, you were the first to ask the question.
Hello, can you hear me?
Hi, yep. I can hear you well. Thank you.
Thanks for the nice talk. My question is, I don't know if this was done, but like, so you are basically producing a selection function, kind of, also for the observation of massive black hole binaries, in the sense that if I observe a binary, then it's more likely that it's coming from, say, a galaxy that is not spherical. So can we actually use this selection function? Do you think we can use this selection function also when doing EM follow-up? Like, say that we have a lot of possible sources and we can exclude some of them based on this, right?
I love your question. Let's just, sorry, I rushed through so much and it's a very early morning for me, but let me just take a step back and say that, remember, binary black holes themselves and galaxies haven't been discovered yet. So when we say, you're absolutely right, there's a selection effect, but the selection effect is that we look for galaxies that have well-measured properties with a central black hole. And then we drop a black hole in a simulation that has a certain mass ratio or a certain distance. So that second black hole, not observed. However, your intuition is right. I think what we can do is say, well, if this system is very spherical, or it looks like it has a core at the center, or it's not rotating, we can say that that galaxy is more likely to have, if there's a merger in that of black holes in that system, that merger would take a long time. Hopefully that made sense. Did that help a little bit?
Yeah, thank you.
Perfect, thank you.
Okay, any other question? So I have one. So this relation, yeah, it's indeed interesting. So my question is this, prediction based on some physics or totally empirical?
This is empirical. There's some things that help me to recognize that it probably is based, it has a physical basis. And this helped me because I'm always worried about the simulations having a numerical problem. But this is kind of a well-known relation saying that the hardening rate is very related to the stellar density in the velocity dispersion too. We didn't have that in this model, but actually it's tucked into V rho over sigma. So the fact that this is so tightly correlated make me think that even though it's empirical, it likely has some physical basis and is not just numerics.
Okay, so you are saying that the qualitatively consistent. Okay.
Yes.
Sounds good. All right. Any other questions? If not, let's thank the speaker again. Thank you, Kelly, for the exciting relation. All right, so let's move on to the last one. So the next speaker is Nathan Stanley from University of Birmingham. He's going to talk about the Bardeen-Peterson effect and its consequences for LISA observations of supermassive black hole binary spin orientations. So Nathan, would you be able to proceed?
All right, thank you very much. One second. All right, can you hear me and see my slides okay?
Yep, both are good.
Perfect. All right, thank you very much for the introduction. My name is Nathan Stanley. I'm a postdoc at the University of Birmingham in the UK. I'm going to talk with you today about black hole spin alignment and disk breaking and the implications for observations of supermassive binary black hole mergers by LISA. I'd like to give a special thanks to Alberto Sassana and Massimo Dodi for very insightful discussions that we had in Milan. I'm doing this work in collaboration with Davide Garosa, who's also in Milan. So generally, supermassive binary black holes, so if you see BBH on my screen, just think binary black hole, please. These binaries are generally expected to evolve in either gas-rich or gas-poor hosts, kind of in a general sense. And the big hope is that the measurements by LISA of the spin orientations will be able to discriminate between these two formation channels. And so these black holes will have a spin magnitude S or dimensionless spin magnitude chi, but we're going to focus in this study on the spin orientations or the spin orbit misalignments, theta 1 and theta 2 of the more massive and less massive black holes respectively. And as Kelly just explained in great detail, there's many processes that are relevant for producing pairs and ultimately bounded pairs of binary of supermassive black holes. And so there's the processes generally are thought of as depending on as being one or other dominant form of angular momentum loss through the evolution of the binary. And larger separations, the pairing of the two black holes is dominated by dynamical friction against the background stars. And then, as Kelly just explained, the lost cone scattering of individual stars by the binary becomes relevant. And then even smaller separations, viscous drag from disk migration can dominate the angular momentum loss if the binary evolves in a gas-rich galactic host environment. And then the baton is finally handed off to the gravitational wave emission phase at the smallest separations, and which drives the binary to merger. So if we start from the assumption, which is a rather generic assumption, that the binary black holes form with isotropically oriented spin directions, which is to say that there's no alignment mechanisms during the dynamical friction phase at the earliest phases of binary pairing, of black hole pairing, then these isotropic spins, if the binary evolves in a gas pore host, then they will remain roughly isotropic, and all the way through the gravitational wave emission phase, which implies that the spin precession experienced by these black hole binaries would be generic, meaning that the orbital angular momentum will precess and nutate about the total angular momentum. And so that's kind of well under, more or less, kind of simpler than the other case, in which the binary evolves in a gas-rich host, in which case the Bardian-Pedersen effect can align the spins during the disk migration phase, but the amount of alignment is very uncertain, and this is going to be the main subject of this study, in which we examine circumbinary disk migration of these binary black holes using a systematic approach to the Bardian-Pedersen effect that was previously published by Davida in 2020 and others in 2020, which the Bardian-Pedersen effect basically is a combination of lens-Turing precession and viscous interactions with the disk. And the setup for this binary, basically, there's a larger circumbinary disk, which is kind of the leftovers of the gas from the galactic merger. And the binary black hole carves a cavity in that circumbinary disk. And little mini disks or secondary disks form around each black hole. And those are the accretion disks. Those are the disks that the black holes are actually accreting from, those little secondary disks. And that's where the Bardian-Pedersen effect is relevant, in which basically what it does is that the inner region of the disk aligns on a shorter time scale to the equatorial plane of the black hole than the outer region of the disk, which is at kind of at the same time working to align the black hole spin with the larger circumbinary disk. And so it's a very dynamical and complicated thing. And over the last decade or so, hydrodynamical simulations of the Bardian-Pedersen effect have shown that if the inclination of the disk is sufficiently large, then the disk can actually break. And recent studies by Rebecca Nealon and others have confirmed that this disk breaking is a physical result of the hydrosims. And perhaps it's worth saying that the model that I'm using from Gross et al. 2020 to model the Bardian-Pedersen effect is a semi-analytical model, which actually does capture this critical angle phenomenon where the disk breaks, in the sense that the evolutionary equations of the disk actually break down and there's no physical solutions. And further subsequent studies show that in the region of the parameter space where these semi-analytic models break down is actually basically exactly where the hydrosim studies show that the disk breaks. And so we can confidently move on and use this model and assume that in the regions of no physical solutions, that's where the disk actually breaks. And so for simplicity, because nobody really knows what happens after the disk breaks and it becomes very, very complicated, for simplicity, in our model, we just are going to assume that when the accreting black hole, encounters a critical disk angle, we just assume that the alignment ceases and we hold the spin orientation constant for the remainder of the gas-driven in-spiral. And so if we look at a simple output of these model assumptions, we have the full in-spiral, we have the in-spiral evolution of the binary black hole spin orientations of the more massive black hole on the left and less massive black hole on the right, through the disk-driven in-spiral phase and the gravitational wave emission-driven in-spiral phase. Starting on the very left, look at the left panel, for instance. Binaries with, so this is the distribution of binary black holes with isotropically oriented spins initially. And so binaries with initial spin orientations that are sufficiently below the orbital plane will experience some alignment and then encounter a critical angle, after which we hold the angle constant until the decoupling separation, which is where this kind of sharp transition to the gravitational wave emission phase begins. And in reality, it's not going to be such a sharp transition. It's going to be more smooth, but we're just trying to encapsulate the essential ingredients here. If the spin orientations of the black holes are sufficiently near the orbital plane initially, then basically the disk shouldn't exist. It is the black hole spin is initialized at an orientation where the disk shouldn't exist, and so the spin orientation doesn't evolve at all during the disk migration until the gravitational waves take over. But if it's initialized with orientation sufficiently above the orbital plane, then the alignment, depending on the other parameters of the disk and the black holes, can align quite efficiently and remain aligned all the way to merger. So there's lots of free parameters in this model, as you can probably imagine, and I don't want to get into the weeds of it. And so it's actually helpful that we can kind of boil down the essential dynamics into two main parameters. And so kappa governs the effect of the companion on the accretion of each black hole, where kappa sub I is the initial kappa, so the value of kappa at the initial separation, which determines if the spin begins, basically, if it begins at a critical angle. So the initial kappa tells you how likely are you to not experience any disk, any alignment at all from the Bardian-Pedersen effect. The other parameter, omega, governs the relative contributions of the in-spiral and the alignment. And so basically a large omega implies that the alignment is happening faster than the in-spiral. And so more generally, though, omega and kappa depend on both masses and spin, on the masses and spins. And so we have two of each for a given binary. And generally, the omega 1 for the primary black hole will not be equal to omega 2 of the secondary black hole. Same thing with kappa 1 and kappa 2. And only in the limit of equal masses will we have the equality of the omega 1 and omega 2 and kappa 1 and kappa 2. Or approximately. And so what we can do is reduce the full parameter space to just 5 essential parameters. We have the two, omega 1 and kappa 1 for the primary black hole, omega 2 and kappa 2 for the secondary black hole, and then the dimensionless viscosity parameter alpha, which is the good old-fashioned Suneyev-Shakura viscosity parameter. And then if we can understand how the spin orientations evolve according to these 5 parameters, then we can relate those to the more physical and measurable parameters, more easily measurable parameters, such as the black hole masses and spins. Here's a figure of some contour lines as functions of the total mass of the binary and the mass ratio of the binaries. And instead of looking at the individual omegas, we found that it was more helpful to look at their sum, which are the blue lines, and the ratio of the omegas, which are the green dashed lines. And kind of intuitively, if you take the ratio of the omegas, it is basically independent of the total mass, but depends strongly on the mass ratio. That's why those green dashed lines are vertical. And the sum of the omegas is rather non-trivial, but it's more sensitive to the total mass of the black holes. That's why those blue solid lines are horizontal. And then the orange dotted lines and the red dash dot lines are the initial kappas for the two black holes, which we see for larger total mass. As you look upwards in this plot, the initial kappas and the sum of the omegas, the blue line, generally increase, which implies that more binaries will reach a critical angle and align more quickly for larger total mass. And if we go to the right of this plot, as the mass ratio goes to unity, the initial kappas become equal. The ratio of omegas also approaches unity, which implies that both black holes will align quickly if the sum of the omegas is large. And so you can imagine there are regions in this parameter space that are more favorable than others to produce highly aligned binary black hole systems. And to try to get a feel for the general behavior of this of the spin orientations, for simplicity, let's assume that let's assume that the two initial kappas are equal. So there's only one initial kappa for now. And let's assume that both of the omegas are equal to 1, which corresponds to a moderate amount of alignment. And in the columns, and so in this mega panel plot, the columns correspond to different values of the initial kappa. So how likely are you to experience, to begin at the critical configuration? And the rows were varying the viscosity alpha. And you see in each of these panels, there's a little black box or a large black box. This black box contains the binaries that have a black hole which is initialized at a critical angle. And so in this plane of the two spin orientations, the binaries are evolving from the blue crosses to the red circles, but the ones that are contained in this black box don't evolve at all because they started with the disk that was already broken. And we're assuming that the angle doesn't evolve at all. And the size, the area of this black box in this plane is proportional to the value of the initial kappa and depends on the value of alpha non-trivially. And generally, if you see in the top row for lower values of alpha, the black box is larger, is relatively large for any value of the initial kappa. And this implies that binary black holes that evolve in low viscosity gas-rich hosts will be difficult to distinguish from those that evolve in gas-poor hosts due to the occurrence of this critical angle phenomenon early on in the binary, early on in the disk migration phase. But as you increase alpha, generally the black box can get smaller, unless you're starting at a very high initial kappa, which is to say you're starting the disk migration phase at a very small separation, and so the effect of the companion is very large, which can induce this critical angle thing. And that's why these left column plots are basically, the black box is so large and there's no evolution there. Next, let's look at the dependence on the omegas, and let's fix the viscosity.
You have one minute left. Sorry, I forgot to tell you. Yeah, 1 minute left.
Can I bleed into my question time a little bit? Is that okay?
Sure.
Thank you. I have a problem of having too many results. And so if we fix the viscosity and instead vary the omegas, as you increase the sum of the omegas, the alignment is more efficient. And so that's why more binaries evolve in the bottom two rows and in the top row where the sum of the omegas is small. And if the ratio of the omegas, which is varied in the columns of these panels, if the ratio is less than 1, then that means the secondary is aligning more quickly. And so these binaries kind of stack up on horizontal lines in this plane, like in this panel in the middle left. Or if it's greater than 1, then the primary aligns more efficiently and they stack up in vertical lines in this plane. Now, putting those things together real quickly, returning to the contour plot, Lisa will likely observe binaries with total mass, roughly, kind of naively, between 10 to the 5 and 10 to the 8 solar masses. And from what we just learned, if the total mass is sufficiently large, then binaries can experience sufficient alignment because some of the omegas will be large. But however, if the total mass is not too large, then few binaries will encounter the critical angle. So this implies that there's kind of like a box in this parameter space that contains binaries that are most likely to be highly aligned and to be observable by Lisa. And I have a little movie here. So more generally, if you choose the total mass, the mass ratio, the spin magnitude, and the viscosity, you can hopefully see how these, here we go, how these binaries actually move in the plane. And so in this case, the secondary is aligning more quickly than the primary. That's why they go up faster than they go to the right. And then they settle down into these kind of well-localized regions of the parameter space. You can kind of cut it into 4s, depending on where they actually started. And so binaries that start in the upper right quadrant will end up having both spins aligned. Those that start in the bottom right quadrant will only really have their primary aligned. Those in the top left will have their secondary aligned. And those that start in the bottom left portion of this region, of this plane, will have both spins that encounter the critical angle, and they kind of pile up near the edge of this black box, which implies that they will maintain misaligned spins until the gravitational wave emission phase, meaning that they will also exhibit generic precession as if they had actually evolved in a gas poor host. And I'm going to skip this and move on to my last slide real quick, which everything I just showed was basically about disk migration phase. But if you take a subset of those binaries that we just looked at and look at how they evolve in the gravitational wave driven phase, they will essentially evolve on lines of constant chi-effective, where chi-effective is this post-Newtonian conserved quantity that depends on the masses and spins. But the mass ratio and the spin magnitudes are constant in the post-Newtonian spiral. And so that's why these things evolve on lines of constant chi-effective in this plane defined by the spin orientations. And the green triangles, so that's shown by these green lines, and the green triangles show the actual spin orientations at 10m, which basically the effect of the gravitational wave emission serves to kind of blur those those subpopulations that we just talked about. And so this work will be published very soon, so please keep an eye out for it. And to summarize very quickly, if we assume rather generically that binaries are beginning disk migration with isotropic spin directions, then there exist degeneracies between the spins of binary black holes and gas poor hosts and gas rich hosts with low viscosity, very high total mass due to the disk breaking, and very low total mass due to the inefficient alignment of the Bardian-Pedersen effect. But otherwise, it can align the spins and create subpopulations defined by whether one or both or neither of the spins are aligned. And these subpopulations will exhibit different spin precession in the LISA band, which will be the focus of a follow-up study. And last but not least, if LISA measures binary black holes with predominantly aligned spins, then this implies that formation in that they formed in a high viscosity gas-rich host. That's all I have for you. Thank you so much for listening.
All right, thank you so much, Nathan, for the wonderful talk. Yes, indeed, it was so many results that you had to show. Very good. So any questions from the audience? I guess we can take one or two. I think I have one quick one. So you showed this QM, plot. Sorry, I disabled my video. Anyway, so you showed this QM plot, yes, and then you had this, multiple lines, and I wasn't able to, understand, these multiple lines, the meaning of these multiple lines. Can you quickly explain that again to me?
Yeah, sorry. I apologize. It's a lot, I know. And so instead of these parameters omega and kappa are very nice because they depend on all the other free parameters of the system. And so we can kind of use omega and kappa as like proxies for how the spin orientations will evolve as a function of the more physical parameters like the total mass and the mass ratio and the spin magnitudes. And so basically the first look at the initial kappas, I think they're simpler, which basically says how likely are you to not have your spins evolve at all because the disk starts off being broken. So the higher the kappa, the more likely it is that you experience this disk breaking. And so these are the red and orange lines here, which are strongly dependent, the magnitude of the kappas are most dependent on the total mass, on the magnitude of the total mass. And so for larger total mass, larger initial kappas, the red and orange lines go go upwards, and you're more likely to begin the evolution with a broken disk, which is to say you're not going to evolve the spin orientation at all.
And then I think I got the essence of this plot. Sorry. Yeah.
And then because there's two things: how likely are you to have your disk break, and then how fast is the alignment, and they kind of compete, right? Maybe you begin with a broken disk, and so you can't align at all. But maybe you don't begin at a broken disk, but the alignment isn't efficient at all. And so that's what the blue line shows: how efficient is the alignment, the sum of the omegas. And so larger omegas mean more efficient alignment. And so there's this box I can draw here to where, you're not too massive, like up here, to where your disk is just always broken, and you're not, too light, like down here, to where the alignment is not efficient enough. And so there's kind of this like Goldilocks region here, to where you don't start out a broken disk, and if the alignment is efficient enough to actually for LISA to potentially observe the aligned spins.
I see. Yeah. Okay.
Yes,
And,
I'm sorry for that. And there was a lot there. I'm sorry about that.
No, it's all right. It's all right. I guess, well, yeah, I see the chat window, Alice there saying, would you like to show the slide you skipped over? If we don't have another question. Yeah, we don't.
Sure, I'd love to.
Yeah, since this is the last talk. Yeah.
Sure. And so kind of, so the question, the kind of like, I guess from here, in this orange box contains the binaries that encounter a disk breaking in the course of their evolution through disk migration phase. And if we want to know how large, if you count how many binaries did this from the whole distribution, in this case, it was about 35% of the binaries will encounter this disk breaking of both black hole disks. And so instead of, if you hold the masses and spins constant and vary the viscosity alpha, and you count those fractions, the ones that have both spins encounter the disk breaking, which is the blue region, it's where both spins encounter the critical angle and thus remain misaligned, significantly misaligned. And then the three other regions are the fractions of binaries that only have one spin that gets aligned, like the primary, I think, is the orange, the green is only the secondary gets aligned, then the red is where both spins get aligned. And so they sit up in that top right corner of the spin plane. And kind of intuitively, just to finish it off, intuitively for low alpha, which alpha is one of these kind of controversial parameters, but if you take it with a grain of salt, for low alpha, that means you have low viscosity disks, and so they're more prone to breaking. And so the fraction of binaries that will encounter the disk breaking kind of explodes. That's why the blue region gets larger. But as you increase alpha, the disks become more viscous and less prone to breaking. And in this case, for the masses and spins considered here, these fractions basically converge to a quarter each, about, because that black box in that spin orientation plane goes to basically a point. Because fewer and fewer binaries are likely to begin at a critical configuration for very large alpha. Thank you for that.
All right. Thank you so much, Nathan. And I think this concludes, well, thank you for the talk, Nathan. And this concludes the parallel session, multi-messenger astrophysics and supermassive black holes for the day. Thank you so much for joining us and watching us, and see you next time. This is the end. Bye-bye.